Good morning, everyone. My name is Eric Person, and I am with International Rectifier, and I am responsible for applications engineering of all of our devices right now, but I'm going to be focusing in the future on GaN, gallium nitride. So today we're going to talk about IGBTs. I know Bill's probably done a great job teaching you the device structure and characteristics. And I'm going to go through kind of the application topics. So essentially the kind of things you need to know in a practical sense to be able to apply these in real world situation. I could probably go on for 8 hours about this. So I've tried to narrow it down into kind of the top items that are important to know when using IGBTs. All right, so let's start with, you've all seen the, here we go. So you've all seen the kind of the equivalent circuit of an IGBT. It's basically a minority carrier device. It's like a giant PNP transistor that's driven with a FET. And the idea here is that the PNP by itself is a current-driven device. So years ago we used to actually use these, more commonly the N-channel devices, and these would be the power transistor. One of the things you'll recall is that you have a junction drop here, so you got roughly a 0.7 volt from, it's actually the emitter of the PNP, but it's called the collector of the composite device. So how confusing is that, right? So it's the collector. In order to be able to draw current through the base, you need to have this is a low resistance MOSFET here. So the emitter here has to be at least 0.7 volt plus some additional drop lower than the collector. So there's no way you can saturate this thing to less than on the order of a volt. All right, so that's kind of a limitation to the on state characteristic of these devices. So before I go too much further, I want to just cover kind of switching in general. I know you've probably seen this all before, but there's a couple of key points I'd like to make on driving, whether it's a FET or an IGBT, but this is an IGBT example. Very commonly, when you're dealing with power electronics, you have an inductive load, right? So this could be part of a converter, could be the magnetizing inductance of the transformer, output filter, or whatever. And the characteristic here is that during the short switching interval, the inductor behaves like a current source. So when you're switching, I know Ned's probably explained the concept that you have kind of a voltage port on this side, and you have a current port on this side. So you're switching voltage here, driving current in this load. And the key thing to remember is that during that switching interval, there's especially in what we call hard switching, there's no way to get the traditional resistive kind of behavior. So what happens is, let's suppose, take the example, I have an inductor here and I have current flowing in the direction shown, right? So where is it going to go? It flows through the diode here in this upper device. So it's basically flowing back to the bus through this diode. So at T0, I'm going to turn on the lower switch. All right. So the first thing that happens, let's say I have 10 amps going through this inductor, and I'm going to turn on the low side switch. Well, as I have 1 amp, 2 amp, 3 amp as it's turning on, what happens to the voltage here? Right? Does it move at all? Anyone? No, it doesn't. The reason is that as long as there's current flowing in the diode, the voltage here will be fixed to a diode drop above the bus. So I have to get all 10 amps before the voltage begins to move. And then the voltage at the output node moves as this device saturates. So of course, if you multiply, this is current, this is device voltage. You multiply the two to get power, and you get this familiar triangle-shaped power loss as you turn on and off. Now, the same thing happens if I turn off relatively slowly. When I turn this device off, first, before any current can go anywhere else besides this device, I have to get the voltage at this node up high enough to get the diode to conduct. So the voltage goes back up, current goes back down, and again you get this loss area underneath the power curve. There are some tricks you can do with very fast devices. You can get zero voltage switching by immediately turning this off and letting the voltage node self-commutate, drive the distributed capacitance here, and eliminate this. And it's probably outside the scope of this topic to go into that detail. But the important thing here to remember is that it's the diode characteristic, which is not an intrinsic part of the IGBT, right? The diode is actually co-packaged with the IGBT. These are two separate die put together in a package. And when I turn this device on, I have to deal with the characteristics of this diode. So this is all idealized, and in real life what you have is that as you pick up this current, I also have to reverse recover the diode. So let me get the blue pen here. So what you really get is you get this kind of a characteristic where this is the diode recovery. And typically then as well, because there's distributed parasitic inductance here, you have a little bit of lead inductance here and here. The voltage at turnoff overshoots, and you get this kind of characteristic, right? So these are all the real world voltages and currents you see with IGBTs. So one of the questions might be, why use an IGBT at all? Why not just use a FET? Because you've got all these problems with minority carriers. It's not a very ideal device, and one of the reasons is that an IGBT, a FET has a linear characteristic in terms of its output behaves like a resistor. So as you increase current, the voltage across it linearly increases. I should really flip this graph the other way here, but with an IGBT, again, because you have that diode drop, and even at very low current, you end up with some significant voltage drop. But as you increase the current, you end up, for the same die size, for the same current carrying capability, I should say, you end up with, at higher and higher load currents, a better effective on resistance. I have a graph I'll show you later that kind of shows it in terms of RDS on irresistively. So they have quite different output characteristics, and the bottom line is that it gets down to dollars per amp, right? I mean, ultimately everything is cost driven, so you can get in a smaller, lower cost piece of silicon, you can get the job done with an IGBT rather than a FET. They have quite different characteristics. The FET is a majority carrier device, so you have lower conductivity per unit area than an IGBT. So in other words, to carry the same current, you'll have a larger die, and I'll show you that in a moment. FET has essentially no carrier lifetime delays, turn on and turn off, but the body diode of the MOSFET does have some dynamic characteristics. IGBT, because it's a bipolar device, you do have dynamic saturation and tail current, but now modern devices are quite good, and you don't really see, these are much less than even 10 years ago. So you can operate IGBTs at 50, 60 kilohertz up to beyond 100 kilohertz, and we'll talk about some of the trade-offs. A FET conducts in both directions, right? So you can turn it on and use it as a synchronous rectifier, whereas IGBT you cannot. So that's one of the drawbacks, you could say. But if you're operating at 600 volts or 1200 volts, that extra volt maybe isn't such a big deal. Resistive versus nonlinear conduction behavior. The intrinsic body diode in the FET. So, you're familiar with that, I presume. It can be very good at low voltage. 20, 30, 40 volt FET has an excellent dynamic body diode characteristic. However, IGBT has no body diode, right? So just the IGBT die is by itself has no reverse conducting. You can make them reverse conducting, and there are companies that offer that. They integrate diodes along with the die, but it's quite a compromise. You typically are better off having a proper diode because you can now use separate processes to make these two different die and optimize them for the application. FETs have avalanche capability, meaning that you can allow the voltage to exceed the breakdown voltage as long as it's driven by a current that's beneath the current limit in avalanche. IGBT, you really can't. They don't have any avalanche characteristics. So you need snubbers of some kind to constrain over voltage. FETs are not necessarily short circuit proof, meaning that if you turn on a low resistance FET into a bus with high capability, the current will quickly exceed the current carrying capability of the bond wires, the die itself, and it will be destroyed within microseconds. Whereas IGBTs mostly are short circuit rated, meaning you can turn them on across a full bus voltage and they will self-protect, and I'll talk a little bit more about that. So I mentioned the die size difference between FET and IGBT. So for a typical, I'm saying a 1 horsepower motor drive, for example, this is not real size, of course, but this is scaled proportionally. FET would be, we use these odd industry die sizes of size 4.6. This is probably a 8 millimeter by 6 by 8 millimeter kind of die. And the IGBT, as you can see, is quite a bit smaller, probably 1/4 the size of the FET. So this is because you have conductivity modulation. You can get very high current densities in IGBT. And the matching diode, of course, now has to be added as well. And these two devices would then be co-packaged into the device you'd buy. And you don't have to have the body diode. There are some applications where you don't need the body diode, so you don't pay for it, you don't buy it. And this is just showing the effective RDS(on). So a FET does have some saturation, so at some point it will desaturate and have a higher on resistance. Whereas IGBT, because it's really more of an on voltage, has this kind of a characteristic of effective RDS(on) versus current. Okay, so just to summarize, comparing the two switches, FET's a majority carrier device. It turns on and off as fast as you can get the gate turned on and off. The speed really isn't usually limited by the device itself. It's limited by the application, by electromagnetic interference and compatibility issues, DVDT, DIDT kind of issues. IGBT is a minority carrier device, so it has some dynamic turn on and turn off characteristic, a little bit of time it takes to get the minority carrier charges going in the junction. The turn off speed is limited by recombination, and the body diode in the bipolar device is intrinsic, and I don't know if I mentioned earlier that at low voltage it's very good. At high voltage it's not good at all. And just to go back briefly to this slide, you can get FETs that have very low RDS(on) at high voltage. It could be half this die size, similar die size. However, the penalty you pay then, these are called superjunction FETs, and that could be the topic of maybe next week's class. The penalty you pay is there's a huge amount of charge in the body diode, so you really can't even use it in an inverter application because there's so much stored charge that you have to get rid of when you try to recover the body diode. So I mentioned that you can reverse conduct, and this can be an advantage if this, again, I'm showing the inductor as a current source. So in any half bridge, if the low side, in this case FET, is off and current is flowing out of the inductor, I have a diode drop. But I can turn the FET on and the channel will conduct, right? So I can make that voltage arbitrarily low. That's called synchronous rectification, and it's commonly used in low voltage circuits. But when you get up to an IGBT with 600, 1200 volt devices, first of all, the IGBT itself can't conduct in the reverse direction, so you have to rely on the diode. So you're going to have that roughly 1 volt drop. And again, as a percentage of bus voltage, it's less of an issue, and it's just one of those things that if you could make a really good FET at 6 or 1200 volt, very low conductivity, and be able to conduct bidirectionally, that would be a very good device. So that's some of the things that look possible using silicon carbide or gallium nitride future kind of devices. So some of the key parameters we look at in IGBT is the breakdown voltage. This is collector emitter, and these are typically bus voltages are commonly either 3 to 400 volt, which is the rectified line. So universal power factor corrected line is in that range, usually 380 to 400 volts. At higher voltage, when you rectify 480 volt three-phase, you have a 700 to 800 volt bus. So the devices are rated at 600 and 1200 typically. Then there are these three, which we'll talk about the trade-off here. There's the saturation characteristic of the device, the VCE on. There's switching loss, which has to do with what I showed you earlier, how quickly you can pick up current and saturate. And then there's short circuit withstand time, which I briefly mentioned, but this is essentially a measure of how long can the device survive with turned on into a bus where you have an accidental short. How long can it do that and survive? And they're typically rated, and I'll show you an example in a minute. So here's the trade-off. One of my other colleagues, Professor Tom Johns at Madison, has this term he calls the theorem of conservation of sorrows, right? So in other words, you always have something you're fighting, and so the good news is, we found a way to reduce switching time, but now the conductivity has gotten worse. So this kind of shows you the three trade-offs that device designers make when they design IGBT. So one is as you try to improve, this doesn't mean longer, this means improved switching time. I'm sorry, it is switching time. As you get shorter and shorter switching time, which you'd like to have for high frequency operation, you trade off on saturation voltage. So the things you do in the device to be able to shorten the switching time negatively impact saturation. And likewise, one of the other things we like to do is be able to have relatively low threshold voltages to be able to drive it easily. But then you have, you trade off saturation current. And likewise, short circuit time is a trade-off. And really, this should be, I'm sorry, this is a mistake here. This should be VCE on. So when you trade off, as you get better in conductivity, you give up short circuit time. So the bottom line here is that when you design a device, you're trying to get improved. You're trying to improve both saturation, switching characteristic, and its ability to survive a short circuit. So on the data sheets, this is how we show conduction loss. Two different graphs here. One shows the IGBT itself at different gate emitter voltages. So this is a classic saturation curve. These aren't typically designed to be operated in the linear region. They don't necessarily behave in a stable manner. You don't have thermal stability across the device to be able to share equally. So these are merely shown as reference. It doesn't imply that you should be operating it in these regions. But this kind of shows the trade-off, the VCE on versus applied collector current. And normally you're only operating on one of these lines here where you have full gate enhancement. The diode, on the other hand, this is just the intrinsic diode characteristic of the forward voltage drop versus the applied current. And notice that they behave quite differently over temperature. As a matter of fact, the voltage is higher at low temperature. This is the -40, this is the 175. So you can end up with situations where you don't always get good sharing between devices. In other words, as one device heats up, if you have multiple die in parallel, as one heats up, it hogs more current, and therefore you can get hot spotting. The way we define switching loss in the IGBT is, again, through a series of graphs. These are one interesting note I should make here, and let me grab a earlier slide, is that when we define switching loss, let me put this one back up for just a minute. We're talking about this circuit. This is the half bridge, which is the most commonly used application circuit for IGBT. So when I define switching loss here, I'm assuming an inductive load and the matching device on top. So it's this body diode and this IGBT that we're referring to when we do these graphs of turn on and turn off losses. Okay, so and losses are represented as an energy per switching event. So this is in microjoules at a given bus voltage. So usually it's at V bus is 400 volts, for example. It's specified on the data sheet. And you can see that turn on and turn off energy is a function of current. And we have different graphs depending on temperature. Right? So there's many variables you have to deal with. And usually you can use simulation models to help understand the losses as you're trying to design with these devices. It'll help you see where the losses are occurring. And then this is just showing for other parameters, for example, as you change the gate drive resistor. In other words, so at an RG of here 4.7 ohms, you have higher losses than at 50 ohms, which might seem confusing, but it has a lot to do with the diode reverse recovery. As you drive harder and harder, you end up with losses showing up. Let me pull this back again. If I have a relatively slow diode and I'm turning this device on, the losses appear here in this device rather than the diode, right? So that's what, it's hard to characterize the IGBT by itself as a, its own body diode. So it's always assumed that the circuit is a half bridge and that you're using the IGBT with a corresponding device on the opposite side. So let's talk about safe operating area. So there's two curves that are shown on a typical IGBT data sheet. One is called forward biased forward SOA, and the other is reverse SOA, which is also the switching safe operating area. So this shows, if you've never seen safe operating area before, we have the collector emitter voltage on the horizontal axis and collector current on the vertical axis. So in this region here, you just can't get there. There's the device intrinsic on characteristic doesn't get you into this region. So this is kind of the limit when you're in the on state here with full gate enhancement. There's an upper limit. The dotted line across the top represents the absolute maximum current the device can handle. Beyond that, all bets are off. And then the vertical line here represents this is a 1200 volt device, so you can't exceed 1200 volts or you end up with device failure. Each line in between here then represents a line of constant power. If you look, this is a log scale, so at every point along here, V and I are, the product of V and I are the same. But it's actually energy because each of them is correspondingly tied to a time duration. So what that means is that for a very short time, for 2 microseconds or less, I can have full 1200 volts and more than 100 amps simultaneously through this device, right? But not for long, right? It gets hot quickly. 10 microseconds is this line, 100, and so on, and all the way up to DC. Now, not every device has a DC line forward safe operating area because sometimes you end up with a device that cuts off like this because of what's called thermal instability, where you don't have equal sharing across all of the millions of devices paralleled on a single die. The reverse bias switching SOA is essentially kind of the same curve, but in that case, we don't bother with the these lines of constant power. You don't, when you're turning off, the gate's already off, so you don't operate partially turned on. All right. Let's talk a little bit about the short circuit rating. So most of these devices are rated for short circuit capability. The reason for that is that, take the example of a motor drive where, here, let me draw for a moment here. So when I have an IGBT half bridge, if this is in a UPS system or some inverter, and I have an inductor and I have an output capacitor, and this is going to the outside world here. If I short this point to either to ground or to bus, I have an inductor here that's buying time essentially, right? So if I'm driving, let's say I short to positive bus, and therefore current's going to be ramping up this way. The inductor buys time, so I usually have current sensing somewhere, back here in the circuit. I have some kind of a resistive shunt. I'm measuring current, and I can detect that there's a problem and do something about it, right? But in the case of a motor drive, typically the inductor is the motor, right? And so on the drive, you have, there's no inductor. This goes to the outside world to a big screw terminal that someone can misapply and get a screwdriver across. And so you can end up with a short either to negative bus or positive bus or earth. But the thing is there's no inductor here. So when you turn the device on, as fast as it turns on, you're going to have current immediately through the device, a fault current. So in any application where you don't have this inductor necessarily between the output of the voltage source inverter and the real world, you need to have short circuit capability. So you can do that, and the way it works is that essentially the gain of the PNP and the on resistance of the FET are scaled so that the maximum current is limited, and it's somewhere in this range of about 5 times the rated current. So a 20 amp IGBT die will run up to 100 or 120 amps, let's say. We don't guarantee what that limit is. All we say is that it'll survive for, typically it's 5 or 10 microseconds. It depends on the technology. But there's a penalty that to get that capability, you end up with a lower, you give up VCE saturation, so you end up with a 400 millivolt penalty. So in other words, if you don't need short circuit capability, you get a more efficient device and better, better dissipation by using a device that isn't short circuit rated. One of the technology trends you'll see in IGBTs is that they're becoming thinner and thinner. 10 years ago, the wafer was 300 or 400 microns thick. Now it's maybe 50, 60 microns. So you can actually, it's like a piece of paper. You can fold it, when you look at the die, the full wafer, it's amazingly thin. And if you think about it, I'll do some bad artwork here again for you. When you have a die, let's say this is the thickness of and this is silicon here, and you have all this junction engineering going on the top. So this is the epitaxially grown silicon, and it has the trenches in it and so on. This big chunk of silicon doesn't really help you dissipate power. I'm creating power up here in these junctions. I need to spread that heat out and get it to the back plate, which is this big thick slab of copper, right? I have to travel through the silicon. So if I have thinner and thinner silicon, I'm better off thermally. So for the same die area, I can dissipate more heat. There's quite a bit of work going on right here on how you attach the die to the copper as well. Techniques, normally they've been soldered for years and years. But solder now, if you look at a modern IGBT that's, let's say it's 70 microns thick, and I'm just drawing a cross section here, and here's all the junction engineering on top with the trenches and so on. The solder itself is about 50 microns, and then you got the back plate. So this becomes a limiting factor. So the technology trends now are to make them the die thin, of course, but then to use techniques like sintering. So this becomes 10 microns instead of 50 or 60. So some interesting work going on there. All right, so when you apply, I'll just show you some waveforms here and some issues that can occur when you apply short circuit. What you're looking at here is green shows the gate drive going to the IGBT. The red is the current at 50 amps per division, and blue shows the VCE of the device. And then the pink is sort of the integration of V times I. This is the energy dissipated. So one interesting thing that happens is, you turn the device on, and at this point we apply the short circuit, right? In each of these examples, when the short circuit is applied, the VCE goes from nearly zero here, this is ground, up to full bus voltage, in this case 400 volts. This is 100 volts per division, okay, 200 volts. So this DVDT right here causes on the device, if you think about the IGBT, on this node, if I have a large DVDT right here, the capacitive coupling to the gate, right? So as this rises, it pulls up on the gate, and you get this spike right here. As the gate voltage goes up, so does the conductivity. So you end up with this huge current overshoot. So this spike, because of capacitance, is what causes this current overshoot. And this is older generation. As we go to newer generation devices, that capacitance has been optimized so that you no longer get that. And it gives us more and more headroom. In other words, we don't have to survive this much current. We can now survive, you round this off. So this is all part of the minute variations that go on in device design and engineering. So, and the other thing is, in the olden days, it was 10 microseconds was barely enough time to detect a short circuit and be able to do something about it. Now, usually short circuit detection is more like in the 2 to 5 microsecond range more commonly. because faster ICs were able to detect and react more quickly. This is just a quick graph to show you what happens. So the blue lines are non-short circuit rated. All right, that's these. I'm sorry. These are short circuit rated, and thus you have a higher VCE on. So the same die, but not short circuit rated, which is these two. So this is 25C, 150C for non-short circuit rated. Same thing, 25C, 150C for a short circuit rated device. And you can see that for the same current at 25C, I give up, let's see, what is this, about 1.8 versus about 2.4. So it's quite a bit of saturation voltage trade-off in order to gain that short circuit capability. It's about 500 millivolts. Quickly talk about gate drive. The goal in gate drive, and again, we're talking most commonly about the half-bridge topology, which is used for UPS, motor drive, any kind of inverters. And there's different ways to do this. One of them is, and I'll show you in a minute, complete galvanic isolation. For lower power applications, commonly the gate drive circuit resides on the negative bus. So you can directly drive the low side. The high side is floating, and it needs some kind of communication here between the controller to be able to drive it. Because this whole thing, as my output flies up and down at 400 volts with ringing and overshoot, that's basically the emitter here. So is the gate, right? This whole thing is moving up and down. So one way to do that is to isolate using some sort of optocoupler is commonly used. So that allows this whole node to float up and down as you switch the output, and you communicate with light, essentially photons, to tell this when to turn on and off. One caveat here is that if I'm directly driving here, coupling through a photocoupler, there's a delay time here, right? And it's temperature dependent, it's it changes with age of the device, and I need to be able to precisely control dead time, so when I turn this one on, I need to make sure this is off first, and vice versa. Otherwise, I get a shoot-through current, right? So now I have to account for the variation in the delay times going through something like an optocoupler. And so they're getting, they're reasonably fast, but they're not nanosecond devices. They're multi-hundred nanosecond devices. So another way to accomplish this same goal is to use what's called a level shifting high voltage IC. So these are high voltage devices. So this whole chunk here floats up and down with your output voltage, and this is all at logic level down here. So these are 600 or 1200 volt devices, all integrated onto an integrated circuit. And this floating high side chunk is able to very quickly, through these current sources, turn the high side on and off. So you eliminate the delay of the photons. What that looks like is, here's an example. This is a photomicrograph of the die, and this is a three-phase driver. Here are the low side drivers, 1, 2, 3, and then these are the floating wells. So these are the three high side drivers, and then the little circles here are the communication transistors that do the level shifting up and down to. So these are all moving up and down at high voltage. This all sits at logic level. And this is a 1200 volt device. So This can all be accomplished in integrated circuits. But many applications require that you have true galvanic isolation. So there are a number of options with integrated transformers. This is an example of analog devices. They make they call it I-coupler topology. It's basically a chip scale transformer right here. So you've got an input side chip, an output side driver. These are both low voltage ICs, and they are connected through a basically an air core transformer. You have very similar from another company, Infineon, makes isolated driver. They call it coreless transformer, but it's essentially the same thing. You've got driver on one side, a receiver on the other, and a transformer in the middle that's all integrated to be able to communicate, and you have full galvanic isolation. One other technology is capacitively coupled. So this is, it seems a bit counterintuitive that given the high DVDTs and the transients and all that you can actually get signals with integrity across a capacitor, but these work actually quite well, and they're very fast. Look at this propagation delay. This is a lower voltage device, but 9 nanosecond prop delay is extraordinary. And the Silicon Labs as well, they have devices down, I think, as low as 10 nanoseconds as well. So these are all good technologies for isolated gate drive. One question though, that even the transformer, it's not sending power, right? It's only communicating from your controller to tell the device to turn on or off. You still need power for the high side gate drive. One way to do that, if you have a bias transformer, like a little housekeeping flyback supply on your drive or inverter, whatever it is, you can add little separate windings here and have one for each of the floating high sides. The penalty is, it seems easy enough, but because of creepage and clearance distances required, the bobbin and everything gets larger, the transformer gets more expensive. So this is not the cheapest way to go, but it does provide a nice stable DC floating voltage. So you can turn the high side on indefinitely, right? I can go to 100% duty cycle, and it's always got power because the power supply is driving it. Another lower cost way to do this is what's called Bootstrap. And the concept here is that I have a capacitor that provides a temporary reservoir of energy, and as I switch the output on and off, when this output is low, when this device is on, I can charge this. I have a better slide here. So when this output, so when the low side is on, let's just say for all practical purposes I'm at 0 here, I'm at about 15 volts here, that's my bias supply. So through this diode resistor network, I charge this back up. And then during the on time, when the high side is on, now this capacitor gives me my 15 volts above the bus, essentially, right? This is, let's say this is 400 volts. When it's on, when the high side's on, this is 400 volts, and I have essentially 415 here to drive this. So, but I have to refresh it periodically because clearly the capacitor can't supply energy indefinitely. So the penalty is you can't go to 100% duty cycle, but you can do 99, which is good enough. And usually that's the, for low-cost applications like appliance drives and so on, that's how it's done. So just the last couple of things here on paralleling. The die itself, the IGBT die is made up of trillions of little cells all in parallel, but they're all processed at the same time, so they're matched, right? When you try to parallel IGBTs on your own, you run into some issues of how well are they going to share current. You have both static and dynamic current sharing potential issues. On the static side, you've got whether the transfer characteristics are matched between the devices. Are they thermally coupled? Are you going to end up with one getting hotter and hogging more and more current and thermal runaway? There's temperature coefficients associated with these. And then dynamic, you have the threshold voltage and the temperature coefficient of that threshold voltage, which is typically not working in your favor. And then you have layout and the symmetry of gate drive that is one going to turn on and off faster than all the rest and be the parallel device that's kind of holding the bag that has all the current at the end and constantly gets hotter. So using a module, you're guaranteed, that all the die inside the module are matched. It's the easy choice. It's the safe choice. You can also parallel them on your own, but now you have to worry about your own matching. Are they from the same date and lot code? Are they processed similarly? Are they going to share well or not? By the way, the Tesla Model S car, which is one of the very high performance electric vehicles on the road today, uses 96 IGBTs. It's a three-phase voltage source inverter with 16 paralleled TO247 FETs per switch, and they're working quite well. But they've done a huge amount of engineering to match it. So just to show you an experiment we did here with trying to perfectly match and then intentionally mismatch devices, we have looking at threshold voltage, on voltage, and the differences between them. Ideal pair, a little bit of mismatch, and then the worst case, which I'll show you here, and you can kind of see on this thermal image that when we try to switch devices that have mismatched threshold voltages, so this is these are the diodes here. Sorry, I can't draw on this, and these are the devices under test. You can see one's quite a bit hotter than the other, and that's because as you increase frequency and as temperature goes up, this device hogs current more than this one because this has a lower threshold voltage. And as it gets hotter, the threshold voltage gets even lower, right? So it's kind of a thermal, I wouldn't say runaway, but it's poorly matched. And you can also see that when you take devices that have poor threshold and poorly matched on voltage, that you end up with poor current sharing. This you can ignore this, but here's the VCE on as these devices turn on, and here are the individual currents between those mismatched devices. And you can see a 2-to-1 difference, but worse than that, the device that takes the most current also has much higher switching loss. So you end up with increased switching loss and higher VCE on, steady state conduction losses so clearly this device here, this blue one, is going to run hotter than the others. And the same thing at turn off, you end up with some very unusual looking behavior. You can actually end up with oscillations here because of thermal mismatches and device parasitics. So, summary. For paralleling IGBTs, the two important parameters you need to worry about are the VCE on and the threshold voltage. If you're able to choose devices that come from the same wafer lot, the same assembly lot, you have a much better chance of having well-matched devices. Having thermal matching between the parallel devices is critical to maintaining their sharing capability. Not every technology shares well because they may not have the positive temperature coefficient. In other words, you have current hogging rather than current sharing. And of course, layout is different, and you can verify all of that with an infrared camera when you look at it under operation. So finally, a summary of what we talked about here. IGBTs, the reason you'd use them as opposed to a FET is because you get basically better cost per amp compared to FET in applications like inverters and motor drives. IGBTs have no intrinsic body diode. They're co-packaged with a body diode when necessary. IGBTs don't switch as fast as FETs because you have minority carriers to slow everything down. But the good news is the minority carriers give you excellent conductivity per unit area, right? IGBTs can have intrinsic short circuit capability, but you pay a penalty for that, which is reduced poorer VCE-on. IGBTs have no intrinsic avalanche capability like FETs. They require, just like FETs, some kind of a gate drive power, either isolated or bootstrap. And paralleling IGBTs requires either derating them so that if you do have mismatch, you can accommodate that, or if you want to optimize it, then you have to buy pre-matched die in a module. Okay, I think we're at our time limit.